In this lesson, you created two plots for conditional means. Let's take a closer look at both of the plots and see how they're different. This second block of code gave us this plot, and this first block of code gave us this plot. Now, you subset this data frame to only consider users who are age 71 or less. So let's do the same up here. Running the code, we can see that we're limiting our x-axis. Now, what I want to do is put these two plots side by side so we can look at them together. Now, you know this before. We basically just save each plot into a variable, and then we plot those variables in one column. So here's the difference between age and age with months. By decreasing the size of our bins and increasing the number of bins, we have less data to estimate each conditional mean. We can see that the noise is a lot worse on this graph since we have finer bin choices. On the other hand, we could go the other direction and increase the size of the bins. Say we could lump everyone together whose age falls on a multiple of 5. Essentially what we'll do is we'll cut our graph in pieces and average these mean friend counts together. So users who are within 2.5 years of 40 will get lumped into 1 point. The same will be true for users who are within 2.5 years of 50 and for users who are in 2.5 years of 60. I'll show you what I mean in code. Here I'm creating a plot with age that's been divided by 5, rounded, and then multiplied by 5. I've also subsetted our data frame just like the other plots. The last thing I'll do is I'll add a geom line with a stat summary. I don't really want to plot the friend count, I want to plot the mean friend count. So I'll pass summary to stat, and I'll pass mean to fun.y. I'll save this plot and add it in with the others. So see how we have less data points here and wider bin widths? By doing this, we would estimate the mean more precisely, but potentially miss important features of the age and friend count relationship. These three plots are an example of the bias variance trade-off, and it's similar to the trade-off we make when choosing the bin width in histograms. One way that analysts can better make this trade-off is by using a flexible statistical model to smooth our estimates of conditional means. ggplot makes it easy to fit such models using geom smooth. So instead of seeing all this noise, we'll have a smooth model or function that will fit along the data. We'll do the same for this plot as well. Here I've added the geom smooth layer to both our first plot and our second plot. I'm just using ggplot's defaults, so all the decisions about what model we'll be using will be made for us. If you're interested in exploring the models and the parameters, take a look at the geom smooth documentation. So I'll save these two plots and then I'll run the code again. So here's our smoother for age with months, and here's our smoother for age. While the smoother captures some of the features of this relationship, it doesn't draw attention to the non-metonic relationship in the low age as well. Not only that, but it really misses the discontinuity at age 69. This highlights that using models like low-S or smoothing splines can be useful, but like nearly any model, it can be subject to systematic errors when the true process generating our data isn't so consistent with the model itself. Here the models are based on the idea that the true function is smooth, but we really know that there's some discontinuity in the relationship.